Welcome everyone to the Winds and Currents webinar. Today we have César Sauvage from Woods Hole Oceanographic, who's going to talk about impacts of surface waves on air-sea flux and marine boundary layer processes. I'll let you take it away, César.
All right, thank you. Share. All right.
Looks good.
Yeah, perfect. Thanks everyone for being here. Thanks for the invitation today for this Odyssey seminar. I know in the audience, some people might have been at the WHOI meeting next week. So sorry if the presentation sounds very familiar. But that being said, so I will talk about for this wind and currents webinar, mostly I'll talk about waves and their impact on air-sea fluxes and marine boundary layer processes. And so this is the work that I've been doing here at WHOI with WHOI, Caroline, and Jim. All right, so today mostly I will talk about the momentum fluxes that we can define as a function of the friction velocity, or as you know, a function of the drag coefficients and the relative wind speed. And especially today, I will focus on the response of the drag coefficient to ocean surface waves through the roughness bands. And so usually this drag coefficient is parameterized in the model. And so we have a lot of different wave-based formulation that exist, and both this algorithm that try to describe this roughness parameter in function of wave age or wave age and slope. So here are just a few of them, and today I will talk about the one developed by Jim and colleagues in 2013, and this is the very well-known and widely used core 3.5 in the latest version. And so this parameterization has been tuned primarily using wave data collected from extratropics, which represent usually region of younger waves and wind waves. And so here I'm just showing the PDF, the distribution of the wave age of the observation that have been used to tune the core observation. So I'll talk a lot about wave age. So just as a quick reminder here, I will define it as a phase speed of the wave over the wind speed. And so the higher the wave age, we'll talk about all the waves and swell. And so the younger the wave age, mostly wind waves and locally generated. So here you can see that most of the waves used are younger, with kind of a peak here around the equilibrium state around 1.2, and then just the rest of the distribution, mostly mixed sea condition and swell. All right. So one thing from here that we can ask is what about swell-dominated region, and especially in the tropics, right? So here I'm showing the global swell probability from 2002. And so what you can see in the tropics is swell-dominated, like about 97% of the time you have a swell in this region. And so particularly I will look at the tropical Atlantic Ocean. And here I'm just showing the wave age distribution for a typical Alberta winter. And so again, you have a first peak here around the equilibrium, but you can see that here we have this bimodal distribution of the wave age with a large second peak here of all the waves, which represent a large proportion of the distribution. And so the question that we'll try to answer today is, can we only characterize the wind stress in this region only using local wind? And I will do core 3.5, and more generally the couple model will represent the wave-mediated air-sea fluxes in the swell-dominated region. So first, let's take a quick look at what core 3.5 is doing in terms of describing the surface roughness length. So it usually divides the roughness into a rough part and smooth parts. And today I will focus on the rough part here. And so one way to define it is a kind of default version of the core 3.5, which is the use of the wind speed based formulation. So the roughness length will be defined using the friction velocity and the Charnock coefficient alpha, which only depend on the 10-meter wind speed. And so by doing that, we're doing some assumption about wind and wave interaction with, we consider only wind seas occurring under high wind and swell only occurring under low winds. And so there is also assumption about wind and wave alignments, which is that waves are always aligned with the wind. But the core 3.5 also has a wave-based formulation, which uses the wave age and the wave slope in the definition of the roughness. And so here more especially the significant wave height, AHS, and our wave age is our CP. And so the phase speed of the wave defined in function of the peak period. So now we are including more explicit wave parameter into the description of the roughness, but we're still making assumption about wind and wave alignment. So we'll try to compare this to simulation, doing some couple modeling. And so I'll use the SCORE regional couple developed here at WHOI by WHOI. And so this is a scheme here representing our couple model. So there is a lot of things going on here, but I just want to point out over a few things. So we have a fully coupled model between the atmosphere, WHOI, the ocean RUMS, and the wave model, WaveWatch 3. And so the idea here is that we have different ways that we can couple the wave to the atmosphere. And today, particularly, I will talk about the way we're using with the COAR parameterization. So we implemented the COAR wave-based simulation into the WHOI surface layer. And so now we're able to send explicit like wave information to the atmosphere. And so WHOI will calculate the new roughness test and stress, taking into account those explicit parameter from the wave model. So I will run different sensitivity tests using either the wave-based formulation called hereafter WDF, and either the wind speed only formulation hereafter WSDF. And so I will try to compare these two. And so to do that, I will look at a study case of January 8th, 2020. And so it was a kind of typical situation where, so here you can see my model here, offshore of the Brazilian coast, and I'm representing the wave age with wave direction. So the idea is that in the center of the domain, you have a more, so younger waves, so in the bluish color. So those waves are locally generated by the easterly trade winds. And then you often have like this situation, like swell coming from the north from further away passing storms, generating waves, and they travel up to the tropics. And so here they enter my domain. This is swell, which is much older waves and largely misaligned. And so it will enter this region of like moderate to high trade winds. And you can also notice this south kind of east corner here with very high wave age. And this is also a location where the wind is very weak. So this is purely swell here, and I won't be really interested into this kind of situation. I will really look at this swell coming from the north and interacting with the trade wind here. So if I were to look at the distribution of the stress for this particular day along the wind speed, so here this is what I'm showing on the left panel. So in black you have the wind speed only distribution, which only depends on the 10-meter wind. So stress is just increasing with the wind and not a lot of variability. And a wave-based formulation in colors. So the colors represent the wave age here. So what you can see is that at lower wind, you have mostly really high wave age and swell. And so as the wind is increasing, you have mostly here in the bluish point, the wind C that is increasing the stress along with the wind. And following quite nicely the wind speed only formulation. And so, which is really interesting is that we can define here what I call the mixed condition, which are this kind of intermediate wave age around 2.5, and which correspond to my swell coming from the north and entering this kind of moderate to high trade wind, which is around like 10, 12 meters per second. And here, what is interesting in this kind of mixed sea condition is that you can see that compared to the wind speed only formulation, you have this large decrease of the stress in this condition. And so you can see it also in terms of spatial differences. So here, kind of similarly, in the center of the domain, you have younger waves, which will increase the roughness and increase the stress. And in the northern part, you have this swell coming in, which mostly decrease the roughness, kind of smoothing out the sea and largely decrease the stress over a large part of the domain, and could be up to 10 to 15%. And this will largely impact the 10-meter wind above. And so by decreasing the stress, you will have a direct effect on the 10-meter wind speed, which will be decreasing up to 5% in this case. So this kind of situation leads to really significant differences in the parameterization. And you can imagine that this is just a snapshot, but if you have these differences every day, then you can, after long enough time, you will start to have a lot of differences in circulation pattern, SST, and so on. So but now what we're wondering is that, okay, so this is just kind of sensitivity test with the model, but is this true? Is this something that we actually observed in the observation of the fluxes? Do we have this large decrease in this condition? So this is what I'm trying to answer here, taking advantage of some observation that we have from a campaign that occurred in this region, the Atomic Urec campaign, which stands for Atlantic Trade Wind Ocean Atmosphere Mesoscale Interaction. And so luckily we had quite a few observation and direct measurement of the stress from different platforms. So we have the Swift drifters, we have autonomous platform like the Ocarina, and some research vessel measurement like the Roundup. And so here on the map, I'm showing you all the different tracks from the observation, and in gray, this is where I sample my model to try to compare with the observation. And so if I were to compare the fluxes measurement to my model, I will have this very nice and colorful plot here, where you can see all the different colors here represent my observation. And then in black, you have the wind speed only formulation, and in red, the wave-based formulation. So what you get from this plot is that I feel like both of the simulation could do a fairly good job in representing the stress. It's kind of in the middle of the scatter. You have really large variability in the observation. So it's kind of just from here, hard to say whether the wave-based formulation is doing a better job or not. And if I were to show you the kind of average of all the different simulation observation, everything will kind of collapse into just one line. So here again, doing that is not really helping me to assess whether the wave-based formulation is better or not. So what I wanted to try next is to try to relate this stress observation to some kind of wave age and sea states. And so I'm going to look at the run here, which track is in blue on the map, which is in the north, and they have like stress and wave collocated measurements. So what I try to do here is that given wind, how much of the stress is supported by what kind of sea state. And so here on this plot, I'm showing so for the run for along the wind speed, and you have the percentage of stress that is supported. And so each line here represents different wave age and sea state. So the red line is for high wave age, about 3, which I consider to be purely swell. And so this generally affects mostly under weak wind. So it's supporting mostly fine swell under weak wind. And then as the wind is picking up, the influence of swell just decrease. For intermediate wave age and kind of mixed sea condition, the peak is around 6-7 meters per second. And then as the wind is increasing, the influence of mixed sea and the stress just decrease. And then for higher wind, about 9-10 meters per second, the most influence will be done by wind sea and equilibrium sea state. So this kind of behavior would be fairly expected, I would say. And so if I compare this to my model, and especially for the case where I have this swell coming from the north, I would end up having a plot looking like this. And I want you to look mostly around 10 meters per second here, where it looks like in the model at 10 meters, 12 meters per second. So the mixed condition and the wind C and equilibrium C state actually influence at a ratio like 50-50 contribution to the stress. So what we conclude from that, so it's very different from the observation. And so there is some kind of bias in the 4.5 wave-based formulation that tend to overemphasize the influence of this mixed sea condition and swell at higher winds. And so by overemphasize the impact of swell and mixed sea condition at higher wind, you will have this decrease of the stress, which is actually not realistic and a bias in this wave-based formulation. So there are different ways that we can try to actually alleviate this bias. And so one way that I'm going to describe today is to actually try to take into account the alignments between wind and waves. And so what we find is that the sea state leading to the strong decrease of the surface wind stress appears to be strongly misaligned. And so here on the bottom left, if we look again at the distribution of the stress along the winds, now the color is the angle between wind and wave. And here to describe the angle, I'm looking at the peak direction of the waves. And so you can see that all the points that lead to the decrease of the stress actually are strongly misaligned with the wind. And so if you look at it on the map, so it's not very surprising. We have this swell coming from the north, which is strongly misaligned with the trade wind, like the easterly, northeasterly trade wind in the region. And just to go a bit further here, I'm showing the full directional spectrum of the waves for two different points. So one in the northern part and one in the center part of the domain. So in the northern part, you can see that most of the signal is coming from this dominant swell as expected, but you can also find some younger waves that are aligned with the wind. And similarly, in the center of the domain, most of the signal is dominated by this young and equilibrium waves following the trade winds, but you can also start to see this kind of background signal of the swell coming from the north. So the idea here is to try to include this alignment between wind and waves in our description of the roughness. And so following previous studies that have been done trying to do that, especially for offshore wind energy studies, we're going to include the cosine of the angle between wind and waves in the roughness formulation, like written here. And so if I were to run again the simulation using this new parameterization, I would have a much better distribution of the stress against the wind speed with correction of the slow bias of the stress induced by mixed condition at moderate to high winds, and which would be in better agreement with the observation. So here, that would summarize kind of our work on the tropics and try to see how the wave-based formulation would behave in this kind of swell-dominated region. So we found this kind of low bias of mixed sea state condition under moderate to high wind. And so we have implemented this kind of new way, wave-based formulation, including angle between wind and wave, and that will help us correct this roughness parameterization and have a much better stress in this region. And so from here, we wanted to kind of expand a bit on this concept of misalignment between wind and waves. But we wanted to go away a bit from the tropics and go a bit further north in the North Atlantic region, where we have a lot of strong storms and atmospheric fronts. And especially today, I will look at the alignment between wind and waves under atmospheric fronts and storm in this region. And so here in this little animation on the bottom right, this is a cold and warm front detection over the North Atlantic. And so this is just kind of showing you the scale and how often it can occurs. It's just the winter months here. So we have this very long along frontal scale of many thousands of kilometers with a very narrow across frontal scale of a few hundreds of kilometers. And from previous studies that looked at cold front climatology from Reese and Kyode, they've found that in this region for winter months, it accounts for 15% of the time. So it's happening quite often in this region. So the idea here during these strong events is that usually what's happening is that we have first a warm front coming with stronger winds, generated local waves that are aligned with the wind. And then suddenly we have this cold front that arrives with a really abrupt shift in the wind direction. You can see on this little scheme here. And so this abrupt shift of direction, well, you're going to end up having a large part of the domain that is where you have wind and wave that are misaligned because the wave doesn't have time to adjust that quickly to this new wind direction. So so what we want is to try to characterize these waves and what are the impacts in this kind of condition on the roughness and the stress. So to do that here, again, I'm gonna run a couple simulation using the 4, so slightly different configuration than earlier. Here I have a nested domain, so a bigger domain, which would be only atmospheric at 7.5, and then my smaller domain here at 1.5 meter horizontal resolution, fully coupled warp fronts wave at 3. And so I will mainly focus on the smaller domain here. And first of all, before looking at the model, I will try to look at and characterize this atmospheric front in the observation, and especially we'll look at the WHOI observation, which is the black one here. And so I will look at a study case here of a cold front passing in December 2017. And so here what I'm showing is just several time series. So the first one here on the top is the wind and wave direction. And then you have the 10-meter winds in black and significant wave heights. Then you have the wave age, and then air temperature, relative humidity, and finally you have the angle and alignment between wind and wave. So the idea here is that you have your cold front passing with increasing of the air temperature. You have the wind start to peak up, followed by the increase of the significant wave height. And you can see that during this time, my wind and wave are aligned. But suddenly we have this cold front here, sudden decrease in the air temperature. We still have young waves here. And you can see that the wind is so quickly shifting from a southerly wind, prefrontal wind, as you can see on the windows on the right here, to in a matter of just a couple hours, 1 or 2 hours, to a north-westerly winds. So really abrupt shift of wind direction. The waves are still fairly young, and you can see here on the angle on the last time series that it goes quickly from aligned to strongly misaligned. And as you can see on the very first plot, the waves and wind stayed misaligned for quite a long time, and especially for this study case, almost over a day. And so here, just a complementary, I'm showing the full directional spectrum of the wave from NDVC mooring, which was close to the WHOI. So the first one is the prefront. So you have this dominant southerly waves coming in, following the wind. And then right after the front, we still have this dominant southerly waves, slightly older, but still there and dominating the sea state. But you can see here that there is this very young wave that start to be generated over the sea state and start to grow following the new wind, but it will take some time for those new waves to kind of take over the sea states. And in this case, again, it stays about 24 hours after the cold front. So very strong, even very interesting features here. And so here, if I'll look at what's so similar thing, but now in the model. So in my model, I just try to simulate this over a few days around the front. So this is my couple simulation. So you can see a kind of similar story, but this time kind of a 2D fields of my fronts. So here on the left side, you have the surface wind speed with the blue square represent my front at one time. And so again, you can see this strong shift in wind direction before and after the fronts here. And so on the right side, you can see the angle. So everything behind the front, all this kind of reddish color is strongly misaligned. And so you can see you have the wave direction here. So strongly misaligned with northwesterly winds behind the fronts. And that take for a very large part of the domain. And so this will eventually really impact, as I said, on the tropics. The more the waves are misaligned, which should increase the roughness in this case. And so increasing the roughness behind the front will increase also the surface stress. So we have a large kind of increase of the surface stress following the fronts over a large part of the domain. And this in return will affect quite strongly the surface wind, which will be reduced again over a large part of the domain. And here I also try to look at it not only at the surface, but also at the wind profile. So I started to look at some wind profile here at the WHOI location. All right, so we have two profiles, pre-front and post-front. So pre-front, you can see that both of the profile in both simulation, accounting for alignment or not, are very close to each other, very similar. But after the fronts, you now have a very consistent difference with when you account for the alignment. So you're reducing the wind. And so most of the largest difference is at the surface, but you can see that we have this constant decrease all along the marine atmospheric boundary layer when including for the angle. So that's very interesting. And so there are more to see on this kind of events. And just before the conclusion, I wanted to finish for this seminar, particularly talk a bit about wave currents interaction. And so I just have one quick slide here, so slightly different configuration, but here what I'm showing is still kind of East Coast domain. Here is on the top left the wind stress and direction and the surface currents. You can clearly see the Gulf Stream here. And so the idea was to kind of try to force my wave model with or without currents. So on the bottom left here, you can see the HS without current with the direction. So very smooth field as expected. And so when we force with the current, we have this kind of strong impact of the surface current on the HS here. So I mean, this is expected. This is kind of what we know, that a lot of the variability of HS is strongly related to the ocean currents. But since we are actually using the HS to calculate the fluxes in the bulk formula, then what would be the impact of this kind of wind, of this kind of wave current interaction on the fluxes? And so this is what I'm showing here on the three different plot here on the roughness, drag coefficient, and then stress. And so this is really nice. You can see like the imprint of the Gulf Stream through the increase of the HS. So especially when waves and current are opposed, you have the increase of the HS. And so in that case, you have an increase of the roughness, of the drag coefficient, and of the stress. So you can argue that the differences overall are quite small, so it's probably not the dominant effect, but I still think it was very cool to see the imprint of the Gulf Stream through this kind of interaction wave currents on the stress. And all right, so reaching out to the conclusion here. So I may not repeat everything. I just wanted to add one more thing. So we found that the core 3.5 wave-based relation had a bias, and especially was overemphasizing the mid-sea condition and swell impacts on the roughness and on the stress, especially for moderate to high wind condition. And so I been talking about one possible solution to alleviate the low stress bias, which is try to include more physics and like the alignment between wind and wave. But there is another way to kind of correct for this bias, which is try to go away for the peak quantity, which tend to really overemphasizes all the waves, and replace that with mean quantity, like the mean wave period, the mean wave age. And so by doing that and calculating the roughness, accounting for average quantity of the wave field, we will also correct this low bias of the spreads. And yeah, I think I will stop here and just open for discussion. Thanks.
Thank you so much. Really nice talk. Are there questions? And maybe while people are thinking of questions, Tom has a question, so I'll let him go ahead.
Hi, César. Really interesting talk. Nice work. Could you flip back to the wave current interaction slide? It was basically your last slide. Yeah. So you said that bulk formulas don't take account of this, but I was confused by that because is this effect mostly coming through the impact on the significant wave height, or is there something else? Because bulk formulas could take account of the significant wave height effect.
Yeah. Well, I guess I guess it depends on what you feed with to the bulk formula, right? It's kind of similar thing as when we think about relative wind speed. Some people would just like feed the wind without taking into account the current. And I think here, especially in the modeling community, you could also just feed HS with seeing the current, and then in your bulk formula, you wouldn't have this kind of wave currents kind of effect. Now, if we're feeding your bulk formula with observation, I guess your HS probably already take that into account. But I guess here I'm mostly thinking about kind of modeling community that would just like feed smooth kind of field of HS. Yeah.
Okay, thanks. That makes sense.
Yeah.
Other questions? I have another detailed question. You showed in switching from the two models, a reduction in spread. So you had a plot of tau versus wind speed, I think. And I just wondered, what's the metric for measuring the reduction in spread?
So
I mean, visually I see it, but I also see that there's a big spread on the right panel, and I'm wondering how you choose to quantify that.
Yeah, well, yeah, that's true. But yeah, I guess here you really have this kind of like cluster that really tends to also kind of drag the mean toward a larger decrease, whereas here the mean would be much better. Also here I just kind of tune it for just like the few observation that I have, so there might be just more work to kind of refine this parameterization here. It's kind of hard. Also, I mean, as you saw here, like the observation has quite a lot of spread too.
Yeah.
So, it's a bit hard to.
It's hard to.
Yeah.
Well, César, I think if you go back to the slide, that second cluster that is stress is low, I think that's about 40% of the total data points. And if you calculate the mean stress of those cluster between left and right, you can see you see this increase in stress by, I don't know, 20-30%, right? So there, I think that's kind of metric that you use in the paper to say quantitatively this is improvement, right?
Yeah, and clearly you're going from a bimodal distribution to a single mode. But well, thanks. Mark Barassa has his hand up.
Hi, César. Nice talk.
Hi,
Have
thanks.
you tried comparing a stress versus stress scatter plot with conditional, say, C states to see whether you're correcting the right stress rather than correcting the wrong stress? I have a second question after that.
Wait, can you rate it? Like, what do you call like the right stress and the wrong stress?
So from these plots, it's really hard to tell
Yeah.
whether you're correcting an error in the wind force stress or an error in the C state in the swell base stress. It's hard to, there's no clear evidence where the error in the stress is. You're inferring it, but you're not actually checking to see whether it's what you're saying it is. So have you done a stress versus stress scatter plot just to confirm what you're saying?
Oh, like the model stress versus observation kind of stress.
Yes. Yes.
Yeah, I mean, I tried, but again, when you have this kind of stress here, and when I look at the wave-based formation and wind speed, it's pretty hard to get something, especially because of the observation. Most of the time, also don't sample enough of the condition I would like to, or just made some assumption like the Swift drifter. I believe they kind of remove like big swell event in this kind of thing to estimate the friction velocity. So I try to, but it's very hard to say something. Yeah, stress versus stress.
Fair enough. All right. Sampling can be a big problem.
Yeah.
Then the second question is for the directional correction, where you're lowering the stress as a function of the angle between the wind and the waves, you're implying that wind-induced short waves are not being created very efficiently. So you're suggesting then that there's some mechanism whereby the waves keep the short waves more organized, aligned with the waves. Is that a correct inference of your findings?
Yeah, I mean, yeah, I think the idea is like most of the shorter waves would most likely be aligned, right? And then when you start to have like mixed sea condition or swell, you're most likely to be in like misaligned condition. So here, I think the idea here in this prime position is like, if you have like perfectly aligned, so the roughness would be just like wave-based formation. And as long as you're going to increase the misalignment between wind and waves, you're going to increase the roughness. And so, of course, if the angle is small, you're not going to do much. But then as the angle is increasing, you're going to increase more. Yeah.
So what's keeping the waves organized, the short waves organized along with the swell? Any ideas?
Yeah, no, I'm not sure. Yeah.
Very interesting stuff. Thank you very much.
Thank you.
Jim Edson, do you want to go ahead?
And just turn on my video while we're talking. Yeah, just a couple of things that I wanted to point out is we are, there's, and I think this is what Mark was saying, is that there's, a couple of things that could be going on here. One, of course, is how accurate is the wave model against observation, right? It could be that you're using this formulation in a coupled model, and there's some issues with the wave component of the model. And we've talked about this, and I know you recognize that, but sometimes it's good to point out with observations, what's what. And the other thing is, again, I think this is related to Mark's question. The core 3.5 algorithm was based, at least the high wind component was based primarily on one data set, Climode, right? And Climode is, it is not a swell. It was in the North Atlantic. It's largely wind-driven waves, particularly at high wind speeds. And so the model was trained for under those conditions, right? Where the peak of the peak of the wave spectrum was still closely associated with the wind waves that are supporting most of the stress, right? And that's why it works fairly well in the North Atlantic, right? What's cool about your study is you're now bringing that down into, the tropical Atlantic. And we're finding it doesn't work so well with that, with the peak phase speed. That makes sense because it's coming from some other, regime into the region, which is why, we've been talking about both your directional correction and the use of the mean wave period, because that's more closely related to the wind waves that are still supporting most of the stress. So I think these two ways of addressing it are important. And, just shows we can always improve these bulk formula, right? And that's what you're showing, which I think is great.
Yeah, thanks, Jim. And here I'm just showing this slide where we use the actual like mean quantity and error, so you would have a much better correction of the roughness and the stress using that in 4.
Yeah, and I guess I'll just make the point, it probably, including directionality I would expect it to improve things. It's just a difficult thing to incorporate. I think we've all sort of struggled with that, with the directionality of these older waves as they propagate into a region where they were not generated. So it remains, I think you're doing great work. You're getting closer, right?
Thanks.
So thanks.
I wanted to ask a question, since we're talking about winds from satellite, and obviously the satellite is responding to capillary waves. So people often think that what a scatterometer is really measuring is the wind stress, and we just calibrate it badly. What do you think the avenues are for going from the study that you've done to really understanding the satellite retrieval and the effects of how capillary waves are seen by a scatterometer?
Right. Well, I guess in this case, I mean, what I've been talking about a lot is like misalignments and younger waves. So I think this happens kind of all the time, this kind of mixed condition, and so this is probably what the scatterometer will measure, and I think that'd be great, and especially as my kind of modeler point of view, to have this kind of fine scale, like temporal and spatial like measurements of the stress to inform and constrain the model, because usually as we've been talking about, all those back formula made a lot of assumptions that are valid for like kind of larger spatial and temporal scale, but as soon as you try to get to finer scale, everything kind of try to fall apart, and having those really high resolution kind of observations would be very helpful to assess all that.
Yeah.
Jim.
Oh, me?
Yeah.
One more thing I wanted to point out that's maybe obvious from this is that, we can do all these things with models and bulk parameterizations, et cetera, but in order to make progress, we have to measure the flux directly. And so we need more. That could be sail drone, that could be fixed moorings, that can be XBAR, that can be, wave riders, et cetera. But unless we have direct measurements of the fluxes, we really can't improve parameterizations, right? You need to have both. And so the community, I know, is pushing for this, but we have to continue pushing for that. We need to have more of these direct measurements. And that's sort of self-serving, but now I'm so busy with WHOI, it's for the rest of the community to push that. But I think I just wanted to make that point, that in order to make progress, we need to measure the fluxes directly.
Thanks. Marcos?
Hi, can you hear me?
Yeah.
So just to add one point to the discussion we just had, just a week ago, 2 weeks ago, in the César workshop, Paco López Decker showed some evidences with SAR data that actually the vertical polarized beam is usually very much linked to the capillary waves. Yeah, but actually on the HH pole, he showed some evidence of more influence of the longer waves. And actually, we're going to take a look at it with scattorometer data, with KU band scattorometer data now, because of course that has also some implications on the wind retrieval, as you just mentioned. So we're going to try to disentangle this potential, let's say, longer wave impact on the horizontal polarized beam. Yeah.
What's your timeline for doing that?
Well, hopefully this year. Yeah. So this is a short-term project. I think to have some proof of this, let's say, signal or signature. It shouldn't take long. So this is a sort of a short-term project, 6-7 months. So hopefully by the end of this year. So if Mark keeps delaying the IOV-WST meeting, we may have some time to present this.
Thanks. Melanie, you've got your hand up. You're
I think
muted.
you're muted. Yeah.
Melanie, you're muted.
Did you hear us?
I'm not sure. Melanie, can you hear us?
Yeah, not well enough apparently. Okay, sorry. Hopefully it's okay if we've entered the part of today's program where it's more of a group conversation, because I was going to comment on what Marcos was just saying. It reminded me of something that Doug Vandemark presented at the Ocean Vector Wind Science Team meeting a few years ago. And I'm wondering if you have thoughts on this, or if Jim Edson might remember more of the details, or Marcos. But Doug showed these horseshoe-shaped features. And since he's a really great teacher, the reason I remember is because he had put a picture of an actual horseshoe on the slide at the beginning and said that later we'd find out why it was related to winds from satellites. But and they were sort of 20 to 30 centimeter features, I think, associated with breaking waves. And I don't remember if Jim was a co-author, but maybe he remembers and can help me out. But I think that he was, I'm wondering if it is associated with the signals that Marcos was just talking about. And maybe no one knows, but I just thought it might be good to make that connection. And
yeah, I remember the horseshoe stuff.
Yeah.
But now my memory doesn't go beyond that, but I remember the horseshoe.
All right. So my comment is that Marcos should look up Doug's horseshoe paper. You can find something online.
Actually, Doug was very active in this discussion as well in the César workshop. So I'll go back to his horseshoe stuff, since we have to do some plenary paper or white paper or whatever. I'll remind him about his horseshoe.
I do have a question for César as well. I guess in terms of practical approaches for right now, while these important subtle issues of how to deal with wave direction and wave age are being worked out, and we're gathering more direct covariance observations, would it be a terrible idea to just use the wind speed dependent formula? Because once you correct your wave-based formula, you come back to where you were without it on average, right?
Yeah. So yeah, I guess it maybe kind of depends on what you want to do. If you're looking for like long-term average, I think you might as well do the wind speed only formulation, because in average it does a pretty good job. So it's pretty worth it to use the wind speed only formulation. Now, if you want to do shorter kind of time scale or like steady case event, you might miss a lot of kind of variability in the stress using only the wind speed formulation. So I think in that case, the easier way would be here to use kind of average quantity of the wave. If if we have it, it's just easier to use it as you said, that including direction and everything. So yeah, I think it maybe kind of depend on what you want to do, but in average, the wind speed only does a pretty good job. So yeah.
Yeah, and of course, it's the variability around that is important that you're trying to fix, right? I'm curious, have you or is anyone looking at the direct covariance data from the WHOI endurance array, where you have the polarizing effect of the coastline on the winds, and you might find some interesting directional differences that are different than the ones in the other area you're looking at?
Well, yeah, that's
more data.
Yeah, that's really interesting. It's on my list of to do things, but I haven't looked at it yet. And so while Jim is here, if you have good data of fluxes, I'll take it.
Yeah, we do have a nice data set from endurance to share.
Great.
Thanks for the nice talk.
Well, I'll point out that Mark has reminded us that all of the history of ocean vector wind science team talks are available online, and he's provided the link. So everybody who wants to hunt down horseshoes can do that. Any other questions today?
César, this is Roger. Thanks for the nice talk. I just wanted to get a little clarification on this plot on the left that's on the screen right now. How exactly did you compute that? What does that represent? I didn't quite follow that.
Well, I guess it's kind of just a simple association. I have like wind and stress measurement, and I'm just looking at, I have collocated like measurement of waves, and I'm just looking like what is like the wave age when the stress is measured from the observation. And I just like separate into different categories to kind of, that's a bit subjective how I fix the limit here, but it's fairly representative of the difference in states.
Okay, so it's kind of a histogram of the wave state
Yeah.
certain wind speeds.
Yeah.
Okay, great. Thank you.
Yeah.
Other questions today? If not, well, thanks, César, for a really wonderful talk that inspired a very far-reaching and interesting discussion. This was a lot of fun today. I'm going to stop.
Yeah, thanks
recording.
everyone. Yeah.